Picture this. You're looking at a photograph of a busy city street. Instantly, without even thinking about it, you know the taxi is close, the pedestrians are hanging out on the sidewalk, and those skyscrapers, they're towering way off in the background. But to a computer, that photograph isn't a world. It's just a flat grid of colored squares. Welcome to this explainer. Today, we are exploring a really monumental leap in computer vision. How exactly we're teaching machines to transform those flat two-dimensional pixels into comprehensive, fully realized 3D world models. We're talking about taking a simple, everyday photograph and giving a synthetic brain the power to truly understand the physical space it represents.
Now, to really grasp the sheer scale of this challenge, we have to start with the fundamental flaw of cameras. When a rich 3D world is captured on a flat 2D sensor, the entire Z dimension, the depth, is completely collapsed. Mathematically speaking, this creates what we call an ill-posed task. Think about it. Is that gray, jagged shape in the image a massive mountain miles away? Or is it just a tiny pebble sitting mere inches from the lens? Because of how scale interacts with distance, that mountain and that pebble can project to the exact same size on the camera sensor. If a self-driving car miscalculates this, yeah, the results are catastrophic. This scale versus distance ambiguity is the absolute core math problem we need to solve to make machines perceive reality safely.
So here's our roadmap for this explainer. We'll start by unpacking the 2D perception gap, see how we historically solved the depth problem, look at how deep learning completely changes the game, explore panoptic segmentation and scene graphs, dive into building 3D world models, and finally, connect it all to autonomous driving and beyond.
All right, let's kick things off with part 1, the 2D perception gap. For a very, very long time, the field of computer vision was hyper-focused on segmentation. That essentially means answering the question, what is it? We developed semantic segmentation to label pixels by their class, like, say, coloring all the cars in a picture red. Then we leveled up to instance segmentation, which actually distinguishes individual objects, giving us car 1, car 2, and car 3. And hey, it's truly amazing that a computer knows it's looking at a red car. But if it doesn't know where that car is in physical space, how can it possibly steer around it? Identifying a category tells us what is in the image, but it completely fails to answer where it is in 3D space. It just lacks the spatial reasoning required to actually interact with the real world.
Which naturally brings us to part 2, solving the depth problem.
Try this right now. Seriously, close one eye and just look around the room. Even with half your vision blocked, you can still easily tell how far away your screen or your coffee mug is, right? That's because your brain naturally relies on 6 monocular depth cues. Perspective tells us that parallel lines appear to converge in the distance. Texture gradient shows us that surfaces, like a brick road, look a lot denser the further away they are. Occlusion is just simple logic. If your hand blocks your keyboard, your hand must be closer. Shading and lighting reveal the 3D curves of an object. Familiar size gives us a scaling factor because we inherently know about how big a doorway is supposed to be. And finally, atmospheric haze makes distant mountains look kind of blue and washed out. Machine vision actually attempts to implicitly learn these exact same biological cues from massive amounts of data.
But, well, before deep learning came along, classical machine vision just copied human biology, specifically our stereo vision. It requires 2 cameras separated by a known distance, just like our 2 eyes. And this method relies on a specific 4-step pipeline. First up, rectification mathematically aligns the images from the left and right cameras onto the exact same horizontal plane. Second, stereo matching searches for the exact matching pixels between those 2 separate frames, much like your visual cortex fusing what your left and right eyes see. Third, it computes disparity, which basically measures the physical pixel shift between those matches. And finally, depth conversion transforms that pixel shift into a fully usable 3D map.
The absolutely crucial point of that entire pipeline all comes down to this single math formula. Now bear with me here. The depth calculation formula is Z equals F times B divided by D. Here, Z is your depth, F is the focal length of the lens, B is the baseline distance between your 2 cameras, and D is the disparity. Hold your finger close to your face and blink alternate eyes. See how much your finger jumps back and forth? That massive pixel shift is a large disparity. Now look at the wall across the room and do the exact same thing. It barely moves at all. That is the formula in action. In plain English, depth is inversely proportional to pixel shift. Objects closer to the lens simply have a much larger disparity between the 2 camera views.
Okay, moving right along to part 3, deep learning enters the chat.
So, the major limitation of that stereo vision formula we just talked about is that it requires highly calibrated, perfectly aligned, and honestly, really expensive dual camera hardware.
Deep learning changed everything by turning depth estimation into a dense regression problem. What does that mean in plain English? Well, instead of just saying this broad area is a car, the neural network assigns a specific continuous distance number to every single pixel on the screen using only one single image. The AI effectively learns to recognize those 6 monocular cues we discussed earlier, generating an incredibly dense, highly accurate depth map from a completely standard 2D photograph.
And the rapid evolution of this technology is just staggering. First, we moved to self-supervised learning. This means the AI actually watches standard video sequences and teaches itself depth simply by predicting how objects should logically move from frame to frame. This totally eliminated the need to feed it expensive laser scan training data. Then came models like MADAS, which trained on so much diverse data that it achieved what we call zero-shot generalization. That basically means you can hand it a photo from a completely new environment it has never ever seen, and it can still accurately guess the depth. No way, right? And now modern AI uses vision transformers to look at the entire context of an image at once. Because knowing that the sky is incredibly far away natively helps the AI better estimate the precise depth of the horizon directly below it.
Let's dive into Part 4, Panoptic Segmentation and Scene Graphs.
A true synthetic brain needs a holistic understanding of context, not just raw distance. This brings us to panoptic segmentation, which unifies our understanding of the world into 2 incredibly clear and somewhat funny categories: things and stuff. Yes, those are the actual technical terms. Things are countable objects with distinct boundaries that get unique IDs, like cars, people, or bicycles. Stuff refers to the amorphous background regions without distinct boundaries, like the sky, the grass, or the road. And honestly, classifying the stuff is just as vital as counting the things. Panoptic segmentation holistically maps an entire scene, answering both exactly what is there and exactly which specific instance it is.
Once the AI knows what the things and the stuff are, and it knows exactly where they are in 3D space, it organizes all that information into a scene graph. Think of a scene graph like a massive relational web. The nodes represent the objects themselves, say a person and a bicycle. The edges of the web are the spatial predicates connecting them, such as the relationship writing. This gives AI incredible contextual power. It fundamentally understands the geometry of the room, not just a bunch of random pixels, enabling a robot to understand and execute a complex command like, pick up the blue bottle sitting next to the laptop on the wooden desk.
All right, Part 5, Building 3D World Models. Of course, computers need a highly efficient way to store and interact with all this newly extracted spatial data. They primarily use 3 distinct formats to build these navigable worlds. Point clouds are kind of like a swarm of floating dots. They're a sparse set of 3D X, Y, and Z coordinates. Great for capturing raw sensor data, but very unstructured. Next, voxel grids. Think of these as basically Minecraft. They mathematically slice 3D space into regular tiny cubes, or volume pixels. This is highly structured but eats up a massive amount of computer memory. Finally, meshes. These are the hollow triangular wireframes you see in modern video games. They create highly compact, renderable surfaces and are the absolute gold standard for computer graphics and virtual reality.
Now here is a massive game changer for building 3D worlds: NeRF, or Neural Radiance Fields. Instead of building a clunky 3D mesh out of triangles, a NeRF uses a deep AI network to represent an entire scene as a continuous mathematical function of light and density. By simply feeding the network a few standard 2D photos taken from different angles, the AI learns the structure so well that it can literally hallucinate and render completely new photorealistic 3D views of an environment from angles that a camera never even captured. It is totally revolutionizing how we capture and interact with environments digitally.
And finally, Part 6, Autonomous Driving and Beyond.
When it comes to deploying these 3D perception models out in the real world, this isn't just theoretical computer science anymore. This is a multi-billion-dollar debate happening right now, particularly in autonomous driving. On one side of the aisle, you have LiDAR. These are active laser sensors that spin around the car, providing highly accurate, millimeter-level 3D point clouds. But they cost a fortune and can actually fail in bad weather like heavy rain or snow. On the other side, you have monocular depth using standard cameras. It is incredibly cheap and completely passive, but traditionally, cameras only provided relative accuracy, not that perfect metric scale you get from shooting actual lasers.
When put into practice, a self-driving car executes this entire perception pipeline in a matter of milliseconds. First, the camera input is captured. Second is segmentation, rapidly separating the drivable road stuff from the dangerous obstacle things. Third is depth estimation, instantly assigning a per-object distance using the deep learning monocular techniques we've discussed. Fourth, The car fuses all of this into a dynamic, full 3D panoptic map. And finally, planning. The car seamlessly maneuvers around a parked vehicle or slams on the brakes because it doesn't just see a grid of pixels. It mathematically knows a pedestrian is exactly 12 feet away.
And this exact same dense perception pipeline goes far, far beyond autonomous cars. It is the absolute foundation for embodied AI and the spatial computing of the future. For a robotic arm to successfully reach out and grasp a fragile coffee cup, it relies entirely on that exact same depth estimation to calculate coordinates in the real world. For an augmented reality headset to properly hide a virtual chair behind your real physical desk, which is a critical visual trick called occlusion handling, it relies entirely on these incredibly dense real-time depth maps. If the headset doesn't perfectly understand the real-time depth of your room, the digital illusion completely breaks.
So, as deep learning models get phenomenally better at extracting perfect 3D depth from simple 2D cameras, aggressively closing the performance gap with expensive hardware, it leaves us with a critical question for the future of AI. Given the massive trade-offs in cost and scaling, is a camera-only vision-based approach truly sufficient for completely safe Level 5 autonomous driving? Or will we always ultimately need lasers to safely map our reality? Definitely something to think about. Thanks for joining me on this explainer.